In this class, we're not going to be using calculus. That was a decision to make it accessible to more people, and the details and the full power of calculus is not necessary to understand most of what we're going to be doing. Good. I also noted that it's not a coincidence that Isaac Newton, when he was inventing physics, was also inventing calculus. Calculus is the most natural language in which to couch many of the things we're doing, and I warmly recommend that you go and acquire an understanding of calculus. You will find that some of the things we're doing will feel much more natural. In the meantime, we're not going to need the full power of calculus, but we are going to want to draw upon a calculus-like approach when needed, mostly to simplify results. So what we want is to use approximate versions of actual physical formulas and expressions that allow us to manipulate them more easily, to evaluate them more easily, and most importantly, to obtain insight as to how they depend on, one quantity depends on other quantities, in ways that are difficult with a complicated expression, but easier and more direct with a simpler expression. And the simplification in question, we've already used it in some of the lecture videos, is Newton's approximation. Here I want to review a little bit in more detail what the approximation is and how we use it. I hope that this will be useful to those of you who haven't seen it in the past. So without further ado, what's Newton's approximation? Newton's approximation is the statement that for reasonably small values of this number x, you can approximate 1 plus x raised to the 8th power as 1 plus ax, and there's no doubt that the expression on the right is simpler to manipulate, to evaluate, to understand than the expression on the left. It's also true that they're not the same, so we can study this by taking 1 plus x, try to use this for the value of the parameter a, say, equal to 3, then we would be stating that 1 plus x cubed is approximately 1 plus 3x. Now, well, for x equals 0, we're in good shape. This is 1 cubed, which is 1. This is 1 plus 0, which is 1. We're in great shape. As x deviates from 1, the precise agreement will be violated, hence it's only an approximation. For example, if you plug in x equals to 1, you find here 1 plus 1 cubed is 2 cubed, which is 8. And on this side, you find 1 plus 3, which is 4. And 8 is not exactly 4, under most circumstances, is not a very good approximation to 8. You're off by a factor of 2. Indeed, we expect this approximation to be valid precisely when x and a are such that the absolute value of a times x is much less than 1. Both a and x may be, one or both might be negative, but if the magnitude of their product is much less than 1, then we expect the approximation to be valid. Here, clearly, when x is 1 and a is 3, their product being 3 is not much smaller than 1, and we're not surprised that the approximation does not hold here. To demonstrate the sort of approximation and to motivate the fact that maybe this is a reasonable thing to assume because I'm not going to prove it, what I've done here is I've reproduced the plot that I showed in the lecture video. We have here in solid, the solid lines indicate 1 plus x to the a, and the dashed lines indicate the approximate value 1 plus ax. For various values of a, ranging from 5 to negative 4, as indicated by the colors, and we've plotted these functions around 0 for the interval of x from negative to positive about 0.1, and you see that the approximation holds reasonably well to within about 10%. And for the smaller values of absolute a, either 1.5 or negative 0.2, we find better agreement. Larger values of a, by the time x is 0.1, if a is 5, a times x around here becomes 0.1 times 5, which is 0.5, and whether a half is or is not much smaller than 1, well, that depends how precisely you want much smaller to be, but clearly, by this time, the approximation is no longer valid to a high degree of precision, whereas here, when x is 1.5 and x times a is on the order of 0.1 times 1.5, which is 0.15, the approximation is more more precisely valid. So what this tries to motivate is that if the power a is not too large and the deviation from 1 is not too large of the thing you were raising to the 8th power, we can use this approximation, and certainly we get a simpler version of this. One quick comment. When we do physics, we're not always going to be presented with the quantities we want to approximate in exactly this form. Typically, in fact, we won't be. Typically, the thing to which we wish to apply Newton's approximation will be given to us in the form of the sum of two quantities raised to some power. The power might be -2, say, if you're doing Newton's law of gravity, and A and B are distances. Of course, A and B need to be two objects that we can add, so they have to be the same dimensions. Two masses, two distances, two energies, something like that. And because they're two objects of the same type, it makes sense to demand or insist that we're going to write an approximation valid when one of them is much larger in magnitude than the other. So I'm arbitrarily going to decide that the second one here, B, is much smaller in magnitude than A. And so roughly, this is almost the same as A. It deviates from A by a little bit. If I can parameterize that, I'll find a way to show to what extent this quantity deviates from A to the 8th power. Right? So this is about A to the A. That's its value when B is 0. But not quite. I want to know how far, not exactly A to the A. B is not exactly 0. I want to know how far this deviates from A to the A. And the trick that I'm going to use is going to be Newton's approximation. The way I render this amenable to Newton's approximation is I write A plus B as A times 1 plus B to the A. This is simply pulling a factor of A out of the parentheses, and then I raise all this to the 8th power. And then I use the awesome power of algebra that tells me that this is A to the A times 1 plus B over A to the 8th power. And now, by my assumption, unless the power A is very large, this quantity here is exactly amenable to the use of Newton's approximation. B over A will play the role of x, and we can use Newton's approximation. Notice that indeed, when x is 0, I find A over A, and so this is about the same as A to the A times 1 plus B over A times A. That's the Newton's approximation, and this allows me to parameterize the degree by which this approximately deviates from A to the 8th power, and the result is what we have over here. The result is that I find A to the A plus this first deviation. This is might be very handy for those who are not familiar or not comfortable with the algebra. This is the way we render the sum of a large and a small quantity. Remember, this was B was much smaller than A when we did this, amenable to the use of Newton's approximation. The last comment I need to make, of course, is that it's an approximation. This is demonstrated dramatically in the plot over here on the right. All I did, this is the same plot as I had on the previous page. I simply have extended the range of x instead of going from negative 0.1 to positive 0.1 over here. This is the range of the previous plot. I've now extended my view, and we see that by the time x takes values of the order of 2, indeed, as we saw, 1 plus x to the 5th is very far from 1 plus 5x, although 1 plus x to the 1.5 is not that far from 1 plus 1.5x. Smaller values of a, the approximation is valid to larger values of x. In general, we will apply this in regimes where it will be very strictly valid. You also note that while I extended it all the way to positive 2 on the right-hand side, I only went a little bit past x equals negative 0.5. Since I was taking 1 plus x to negative powers, I'll leave it to you to guess why it is that I did not want to extend this graph past value of x equals to negative 1. This should make it clear why I really am doing an approximation that is valid in the vicinity of x equals 0.